Some people are really close to the air conditioner. So I want to say simply, we have a ring of charge. We are a perpendicular distance z away from the center of the ring. I want you to take the ring of charge, which has charge q and radius r, and treat this as if it's got a linear charge density, and find an expression for lambda, the linear charge density of the ring. If I want the charge density, I'm looking for total charge divided by total length. You're trying to figure out the length of what? I hope you understand it's the length of the ring. The ring is where the charge is. We're trying to see how much charge is there per centimeter or per meter of the ring. So I replace the top with the total charge on the ring. That one's easy, right? Q. The bottom, on the other hand, is going to be how big the ring is. I'm thinking circumference will work here, right? And the circumference of the ring is 2 pi capital R, because capital R represents the radius of the ring. Our linear charge density. How's that? Is that all right? Okay. Now, once we have a linear charge density, you remember the other things we have to start to do here. Like, we have to break up our ring into lots of little pieces and try and figure out how to set up some mathematics and geometry that can point to each piece of the ring. We have to kind of find some variables that will help us with this. So I've selected this to be where I'm putting my piece of ring for now. Let's see if I can just make that nice and big and kind of focus on it. I know that dq is going to equal lambda times ds, where ds is how big that piece of arc is. All right. We use s for arc lengths. And I need to be able to point to that piece and then be able to point to each piece around the entire circle. Now, because we had right now, I just positioned us here and we're looking down on the ring. Come back here and realize I'm going to do this as lambda r d theta. Yes? This dq is the piece of charge of that piece of ring. That's what I am saying. I'm going to replace it with the charge density and something that represents the size of the arc length.
So what's the difference between dq and
ds is how big in centimeters that arc length is, and r d theta is how big it is still in centimeters, but in terms of the arc length, so how many radians of arc length are subtended. But by multiplying by this, which is in coulombs per centimeter, I'm getting how much charge that is. Okay? Now, a few of you are with me all the way on this, and a few of you probably understand that there's a lot of redundancies in the things we're doing here. And you might not see it yet, but there are shortcuts we could cut into this. One reason I'm being so methodical is so far we're dealing with what are called uniform charge densities, meaning the whole ring has the same charge density. I take a piece here and a piece there, they would have the same amount of charge if they're the same size piece. They don't have to do that. You could be given a piece that is got more charge on one side than the other. And they can make this a function of theta. Because that's how things like stars and the rings around Jupiter actually are. So we have to have math that allows us for that level of flexibility, which is why I'm trying to be so careful about this stuff. All right, well, pictured right now that you need explained. Yes, sir.
Wait, so Z.
Wait, so? We can do better.
So Z is a constant, right?
Z is a variable that we can use in our answer. I don't know what you mean by constant. For this arrangement to find the force on charge Q, it is probably dependent on Z. I would expect that if Z were a bigger number, the actual size of the force is probably going to be smaller. And I also foresee that if Z were 0, the force would be 0. I think that's a reasonable thing to consider. That's what we wanted to start the whole problem with. What are our constraints? But does that make Z a constant? Well, just in the same way that the size of the radius of the ring, is that a constant? Well, yeah, but if it was a bigger ring, it would have an effect on our answer. So it's hard to talk about constant. For the purpose of this calculation, Z can be in your answer. Well, I believe that. So ultimately, we're trying to find not the sum of all of the contributions to the force, mind you. We would like to find the sum of all the contributions to the force in the x direction, because there's a certain amount of symmetry here, same kind of symmetry we've had on multiple other problems, correct? So I really want this sum. And that sum is based on the sum of the total force scaled by the cosine of phi. Correct? Okay. So we're going to work from there, but we don't have anything for this yet. We should probably build something for that. I've seen a lot of that out there, and a lot of it's good. So let's talk about what we would build for that. Give yourself a little space. I'm expecting that you use Coulomb's law. So Q would be there, right? This charge. And we are saying that this is a piece of charge, so that would be there. K would be there, and my separation distance of r squared would be there. Just building the integral right now. So r can't be in our answer. We know that. Phi can't be in our answer. But our next step is to do substitution. Now we've done this many times before. I've been building this problem up from small pieces for a while. So now we can start our substitution. I saw this on a lot of papers, so this was good. First, recognizing that we're going to take r squared and use the Pythagorean theorem to come up with something that's in terms that we can use in our answer. So that was probably the first substitution. And a lot of you jumped to that one pretty quickly. And you have r squared plus z squared here. Also, a bunch of you realize that we can't just use cosine phi, so you did the extra part and found out how to express cosine phi in terms of your given variables. All good so far? Keep going. We took a little while to build this, but remember, it's got to be a density times a size. So we could do this substitution, but then we're expressing it as an arc length, so I'm going to do this substitution in place of dq. That all good still? Baby steps, right? This represents one piece of the total force. We want to add it up for every piece. Have I left anything out? So I can continue? Because when I look at this, a lot of this doesn't change as I go around the ring. As I choose every piece of charge, does R change as I go around the ring? No. Does Z change as I go around the ring? We're just talking for the purpose of the sum. We're talking about the things that are different as I go around the ring. Does Q change as I go around the ring? Does lambda change as I go around the ring? I think we've handled. We know K doesn't change and Z doesn't change. So all of these things are the same for every piece of the ring. Correct? Well, let's bring all those together. I think there's an R in here, I've forgotten. All right, so you may not understand this part, but R d theta is the length, right? D theta is a piece of angle swept out along the ring. R d theta is how long the actual arc of ring is. But R is the same for every one of them. So if I was adding up lots of arc lengths, I could factor the R out and just add up all of the angle measures. That's what this is saying. Now, if you don't like it, we can leave the R in there and make that part, but it's not going to change what the math says to do next. And the math says if I want to sum up all those pieces of force, I just have to sum up all of the pieces of angle. Now, some of you got stuck right here. You were able to set limits because we talked about the fact that we're going all the way around the ring. Fine. Let's set those limits. But ultimately, we're just adding all this up. We're starting at angle 0, and we're going all the way around the ring until we reach angle 2 pi. Right? We have to include every piece. Now, what we do next, let's just look at that for just a minute. The only thing that matters there is this. This is the only thing that I have to worry about for the time being. Now, this is calculus I want you to be able to do. If you're in mechanics, you could do this. If you aren't, you may not. I don't care. You need to learn this. And so for those of you who don't know what to do next, you should be taking detailed notes. But this is a polynomial. If there's nothing in front of the theta, the d theta, then we assume it is theta to the 0 power. Now, a lot of you already know to do this and know what the result is, but for those of you who don't, this is the polynomial rule, and you need to learn the polynomial rule. Regardless, the polynomial rule is pretty easy to understand, and it's secret sauce. You don't have to know what goes in it. You just have to know how to perform it. I'll let calculus teach you how to do it, and that's what later this year will be for some of you. But you need to find the antiderivative of a polynomial. And I'm going to, just to the side, make sure you understand that the antiderivative of a polynomial, taking this antiderivative, you take whatever the exponent is, and you add 1 to it. You take your new exponent, and you put out in front. This becomes that. That is the polynomial antiderivative rule. It works for any polynomial except those that have an exponent of -1. For the ones that have an exponent of -1, the math don't work, so you have to divide by 0. You'll need a different rule. But for every single other exponent, it works just fine, and that's how it's done. If your exponent's negative, and when you add 1 to it, it stays negative, then suddenly your antiderivative will have a negative sign out front. That's the way it's supposed to work. We have theta to the 0 power. My antiderivative will be theta to the 0 plus 1, and then out front, 1 divided by 0 plus 1, evaluated from 0 to 2 pi. Any questions about that? So those of you who didn't write this down knew how to do this. All right, so let's go back over to our work here and realize that this will now be Q lambda K Z R over R squared plus Z squared to the 3/2 times theta evaluated from 0 to 2 pi. Now, evaluating, we talked about this also. This just means you put in the top boundary and then subtract when you put in the bottom boundary. Pretty sure that's going to just be 2 pi then. So 2 pi Q, K, Z, R, all over R squared plus Z squared to the 3/2 power. What?
You forgot lambda.
I did not forget. It's right there. But I can't have lambda in my answer anyways. So I will have to substitute in what I know about lambda. Lambda is not considered a fundamental constant. It's a constant we created for the purpose of the problem. So we will now have to sub it back in. So Q over 2 pi R. Now, the next things should not surprise you. They will, I guess, but 2 pi R cancels out. Sorry to bore you. And this, I think the order that I want to write this is, I mean, I hope it will be helpful. This is the size of the force. It has all the pieces I would have expected, just like before. And I want you to compare that to the 2-point charges. This was the answer to the 2-point charges. You notice it's exactly the same, right? It's not an accident. All the symmetry has to be preserved here. The only difference is that there's 2Q because we had 2-point charges of value Q. While in this case, we just had one ring of value Q. But the whole geometry was exactly the same. In fact, if you take your ring and kind of put a plane through it, it just shows up as 2 little dots, each with an amount of charge dq. The fact that we add it up to get the total charge, that's not accidental, it's how it works. And notice, this thing does all the same things that this thing does. It's the same term. Because all the geometries were the same. And because all the geometries were the same, we get the same answer. Now remember, we did the point charge problem twice. Once when both charges were Q, and once when one charge was Q and the other charge was negative Q. And I said I wasn't going to do that one, you should do that one. Rework the problem. All it changes is one thing. It changes the cosine to a sine. You should try this here. If half the ring was positive Q and the other half was negative Q, work the geometry again. From the beginning, from scratch, without looking at your notes. Because there's only one ring problem. So once you have mastered why this problem looks the way it does, you can employ it anytime a ring problem is given to you. There's only one two-charge problem. Once you've done it, you can do it. It's going to be the same as every other two-charge problem. You have to understand, there's not that many different geometries that we can do. Once you have mastered the few that you can do, they're all going to work out the same. All the geometries are going to be the same. So I'm encouraging you to look for the similarities, but you need to go tonight and sit down. Sorry, let me say again. Is it, how do I want to say this? Well, I'll say, is it not lost on you that at this moment right here, if I had a circle and I tell you that its radius r, is it not lost on you that I could break this up into little pieces, each with length ds? All right, we've talked about this already, that this is a piece of the arc, and then this ds would be equal to r d theta. Does that make sense too? We've talked a little bit about that, right? If I added up all of these, all the pieces, I would get the length of the arc, correct? That would mean just taking the sum. This would be 0 for a whole ring. I would get the length of a ring. And I would have to start at angle 0 and go all the way around the ring until I make it to angle 2 pi. What's the result of this produce? You understand that if you're really paying attention to what's happening here, the result of this is going to be 2 pi r, because the length of a ring is its circumference. Right? That shouldn't surprise you. In fact, I'd call that a proof. Like, where did circumference come from? I mean, they had to come up with the formula for it. How do you think they came up with the formula for it? I mean, where do you think this comes from? We should be able to prove it in a similar way, right? You guys from mechanics know that you can. You can prove this. Well, you understand that the very next thing I would like to do would be the force on a charged particle from a disk of charge, which would require that we add up every piece of area from that disk and its effect on the charge. That's actually quite a difficult challenge. One that we can do, but it's going to push us in new directions. So the sums have to work. The math has to work out. And there should be some things that you are seeing in here that do work. Now, I've got a group of people in the room who have never done this before. How many of you remember, though, us solving for the area of a disk using the calculus from last year? Okay, so that seems like something that would be appropriate for us to do if we're going to start doing two-dimensional shapes. Now, this is not a physics discussion. This is the math discussion. But this is what's going to be necessary. What I'm going to teach you right now isn't the calculus. It's the physics part of it. What we're going to need to do for a two-dimensional shape. You guys remember this from last year. Remind yourself. Don't listen to me from this point forward. Do the problem. Find out, set up the integral that would give you pi r squared. You guys who have never done this before, we're going to try it. We're going to do it together. So I want to start with a disk. So I'm going to put a disk out here. I'm going to mark the center of the disk. And I'm going to say that this disk has radius r. All right? You guys who have never done this before, we're going to talk about what it would take to add up all the area. So I'll remind you that area is just length times width. We're going to break this thing up into lots of little pieces, all of the same size. And we're going to add up all the pieces. Everybody good with that? I'm going to make a piece right here, a little square of area. In the future, we're going to take that area and multiply by a surface density. So we can integrate over the surface of a charged two-dimensional shape. But for right now, we're just going to see how to set this up. I have a small square, and one side is its length, and the other side is its width. All right, so the area of this small piece is length times width. However, like anything else, like in all of these problems, we need to find a way to express this geometry in the form of a sum. So we're gonna come up with some reference points for how to point to this particular square. So we need to apply to this problem some coordinate, something to help us out. So I'm gonna say that right at the very top that this is 0. I'm doing this so I can have a point of reference. So that's 0. And I want to point to the inside corner of this box. I want to define it. So I need to find a way to point to it. So follow along with me, okay? I'm going to go, oops, I didn't mean to do that. I'm going to go, get back to where it was. I guess that's the way it is. Mr. Shelton, there we go. Now we got it. I'm going to go over and a little bit of an angle, theta, and I'm going to go out a distance r. Now, between these two measurements, is it possible for me to use just those two measurements to point at every single box that would make up this disk? Because I think along this length is a whole row of boxes, right? The first box would be at r equals 0, and the last box would be r equals the radius. And there's a row of boxes all the way there. Would you agree? And there's a similar row of boxes out in this direction. That would be a different theta. And a similar row of boxes out in this direction. That would be a similar theta, right? So for every theta, there's another row of boxes. Can I use theta and r then to point at every single box? I think I can. I have boundaries. I want to make sure that my r goes from the inside all the way to the outside edge. And I want to make sure I start theta at 0 and go all the way around the disk. So my theta is going to start at 0 and go to 2 pi. So those are the limits or boundaries of my integrals, my summations. But that doesn't help me express the shape of this piece here. I need to find a way to find area. I need to find a way to do length times width. So I want to express the length and the width in terms of r and theta. That's what we have to do now. All the same things we did before, but now in 2 dimensions, not 1. For example, I pointed to the inside corner of the box by going over a distance theta and out a distance r. I think this length is just a little more in the r direction. So I'm going to call this length dr. Go out a distance r and then go out a little more. That's the length of that piece. Any question about where that came from or why I'm using it? It's a long r. I'm just going out a little more. I can't make a straight line at W, but I can make a small arc that represents W. Does that make sense? It'd be close to a square. Remember, these are supposed to be super small. So I'm going to make a small arc length there. It's going to be based on the radius of r, but the arc length will be in the theta direction, so r d theta. So I'm sweeping out a little arc length here, and I'm making a piece of r there, and those two will define my area. In fact, my little piece of area, dA, is going to be dr, the length, times r d theta, the width. Any question about that? So what I want to do is add up all of the pieces of area. That's what I want to do. So I need to add up all of the r's and all of the thetas. Now, setting this up, not terrible, but there are some steps now that we didn't have before because it is two-dimensional. First step, I have to sum twice. Once for the r's and once for the thetas. I think the bell's probably supposed to have rung. Also, I have to put the terms that have r with the dr and the terms that have theta with the d theta. Since I'm just multiplying, I can multiply in any order I like. And then put my limits. I would strongly encourage you to see this all the way through. You know the answer, it's going to be pi r squared. Prove it to yourself. I promise it will work. All you need is the polynomial rule that we just did. All right. Some difficulty in envisioning this. I'm just going to look down the length of that picture. So we're at charge Q. That okay? This is the line that I put there to represent its radius. And we're looking at the piece over here and saying that this piece is ds long. We need to use some geometry that will allow us to point to every single piece of the ring. There are shortcuts for doing this that mathematicians know about, but I want you to have the experience of learning how to set this up. So, if it were me, and I'm trying to explain to you, how do we do this? Well, we always pick the place that we use as our reference point, something that we called 0. And in the other examples, we use the middle of the bar or the middle of the arc. Do you remember that? We don't have a middle, so I'm just going to pick a place and call that 0. And now I want to describe where my piece of length is relative to 0. I think I'm going to use an angle measure and a length. I think I'm going to describe where that piece is by saying that piece is angle theta from 0 and a distance r away. I'm pretty sure I could use that to point at every single one. In fact, what I'm doing, I hope you realize that, is I'm using the exact same geometry as the arc to point at every single piece. Because I know then that I can set my theta at 0 and increase it small amounts of angle until I go all the way around, taking in each piece of arc till I get to 2 pi. This is the hardest part. And it's hard to conceptualize, but do you realize that by keeping r the same every time, I can point at a piece here by changing theta to one value, and here by changing theta to another value, and so on and so forth, all the way around until I get here. You follow that so far? In fact, what I'm going to do is say my ds is going to be r times d theta. I'm going to convert ds into an arc length in terms of theta. That way I can point to each one by integrating around a circle. So what I have to do is make sure that when I'm all the way done, when I've set up my geometry, I'm only left with things that are in terms of theta. That way I can add up every piece. And my first theta is going to start at 0, and my last theta is going to be 2 pi. Those are the limits. I'm going to go from here all the way around back to here. And that will give every single piece of arc length. We all right with all that?